So now we'll explain how we are going to calculate the impedance and phase angle of a series resonant circuit. So up to now we seen the circuit like a resistor and an inductor and a capacitor. These three are connected in a series with a source. So whenever for this circuit if resonance is occurs, then that is called as a series resonance circuit or series resonance. So in this series resonance, how we are going to calculate the impedance? How we are going to calculate the impedance and phase angle of a particular series resonance circuit. Now we'll see. Series resonance circuit. So we already know what is the impedance, Nana? What is the impedance of this circuit? Here impedance is nothing but the total resistance of this circuit. So total resistance, nothing but this is a resistance of a component and here this is a XC or XL. XL is a reactance component of an inductor, XC is a reactance component of a capacitor. So what is the total impedance of this circuit? Particular resistance value and reactance of the inductor and reactance of the capacitance, that will become the total impedance of the circuit. So here we can write like this: Z is equals to, we are going to calculate the impedance. So impedance Z equals to, so what is the resistance here I taken, that is, let us take that is R, and here I am going to take this is as a JXL, which is a reactance component. This is JXC. Okay, so but we already know what is XC here, which is 1 by omega C, which is a inversely proportional. So always we should
minus
take
JXC.
negative JXC. Okay, so here total impedance of this circuit is nothing but addition of the resistance as well as the inductor and capacitance. So R plus JXL minus JXC. Here this is a inversely proportional, so we are going to get the negative. So J is common for both. So R plus, take J as common, XL minus XC. So this is the total impedance of the circuit. So what is the impedance? Nothing but if you want to calculate the magnitude of this particular circuit. So for example, X plus IY. In order to calculate the magnitude, what is the formula magnitude? That is under root of real part square plus imaginary part square. What is real part here in the X plus IY? That is X is a real part, that is X square plus Y square. So this is a magnitude for the particular X plus IY, which is a complex conjugate number. So above equation you observe here R plus J into XL minus XC. So here R is a real component, XL minus XC is a imaginary component. So can you calculate the magnitude of this particular impedance? So magnitude of impedance is equals to under root of real part square. So real part square, that is resistance square, plus imaginary part square, that is XL minus XC whole square. Okay, so this is a impedance magnitude of the particular series resonance circuit. So we can explain this with a graph. So here graph I am going to take. On the x-axis, let us take the frequency. X-axis, let us take the frequency, and y-axis I am going to take the reactance. Reactance is nothing but either it may be XL or XC or impedance. So here we are going to take XL or XC as well as Z, that is impedance. So how the XL will vary, how the XC will vary, according to these two, how we are going to get the impedance, that we can see now. So here first you observe what is XL. XL is nothing but omega L, nothing but which is directly proportional to the inductance value. So XL is directly proportional to frequency, or XL is directly proportional to the inductor value. Inductor is constant, no? So and XL is directly proportional to the omega. So if we have any directly proportional, that graph will be in the linear. That graph will be linear. So whenever frequency is 0, inductance value is 0, XL value is 0. If frequency is increases, that XL value is also increases like this. Okay, increases like this. So let us take this graph is XL. Okay, so same thing. What about XC? XC is nothing but 1 by omega C. So 1 by omega C nothing but here whenever frequency is low, capacitance value is more. Whenever frequency increases, capacitance value will be decreases. So capacitance is decreases. So that is which is in the reverse and a negative value. So negative value. So here from here I am going to start at the initial nothing but F is equals to 0. F is equals to 0. That reactance component will be maximum. So I am starting here. So whenever I increase the frequency, that capacitance value decreases like this, which is in the exponential way. Okay, why I taken negative side? Here reactance of the capacitance is negative, so I taken negative values. So here whenever the frequency is low, reactance is infinite. Frequency is low, nothing but I can write like this. 1 by omega C is 1 by 2 pi fc. You substitute F is equals to 0 here, that is 1 by 0 you are going to get. Xc value is infinite. So infinite means that is negative infinite, here I take it. So negative infinite, that will start from infinite to 0. That Xc value is decreases. But XL value, here same thing. XL is equals to 2 pi FL. So when you substitute F is equals to 0, XL value is 0. You substitute F value is increases, then XL value is also increases in a linear fashion. Why? Because this is a directly proportional. Okay, so these two, by considering these two, you are going to get the impedance. So how we are going to get the impedance? So we already know that impedance we are going to calculate with the comparison of XC and XL. So XC and XL. So XC minus XL we are going to take. XC minus XL. Like this is the equation, no? So XC minus XL or XL minus XC. So first, for example, here I am going to take F is equals to FR, resonance frequency. So before resonance frequency, what is the capacitance, Nana? Before resonance frequency, nothing but that is, what is the condition here? XC is greater than XL. XC is greater than XL ante that graph will be leads. That graph will be leads. Whenever XC is greater than XL, what is the impedance value? Nothing but XC, and a negative sign will be increases. So negative sign will be increases in the equation. Negative value increases means total impedance will be decreases up to the FR. Okay, once again, don't confuse here. I'll repeat again. So whenever F is equals to FR, so F is equals to FR means XL equals to XC at this condition. So before FR, that XC is greater than XL. After FR, that XL is greater than XC. Okay. So before FR, XC is greater than XL means that is capacitive component will be more. So capacitive component will be more means negative part is increases here. So negative part is increases means here Z value will be decreases up to the resonance frequency. So up to the resonance frequency that will be decreases. So here I will draw that one. After FR, what is the condition here? That is inductive component. Here after FR, that is inductive. Before FR, that is capacitive. So here that is XC is greater than XL here. Here that XL is greater than XC. Okay. So here that impedance will be decreases in the exponential way up to here, and then up from here that will be increases in a exponential way. So like this you are going to get. So this is a Z graph, and here we are going to take on the y-axis XL and XC. So next we'll go for the phase angle. So I already told that capacitor will leads the system. Capacitor will leads the system. XL will lags the system. XC will leads the system. XL will lags the system. So so I'm going to draw the graph how the phase angle will be. So on the x-axis I'm going to take the frequency. On the y-axis I'm going to take the theta value. That is a phase angle. So that will lead and lag, that in between plus 90 degrees or minus 90 degrees. Plus 90 and minus 90 degrees I'll take like this. So in middle I am going to take F is equals to F1, that is a resonance frequency. So here before resonance frequency that is entirely capacitive, after resonance frequency that is entirely which is a inductive. So here capacitive for this here, capacitive will leads the system. So capacitive will leads the system is nothing but phase angle will be initially, you can observe here in the above diagram, capacitors, how the reactance of the capacitor that will start from downward and then that is finally decreases to 0. Okay, in the same way up to resonance frequency here, up to resonance frequency, what happens here? That capacitance value will be, that phase angle of the capacitance will be decreases up to 0, and then from resonance frequency that is inductive component, so that will lag by 90 degrees in the exponential way that I will represent here. So which is here before resonance frequency that will lead the system, that is a capacitive system. So that will start from minus 90 to 0, minus 90 to 0, and then after resonance frequency that is an inductive component, again that will increases to 90, increases to 90 in the exponential way. Okay, so here this will leads the system. Why? Because this is a capacitive component, and here this is a lags the system, so this is an inductive component. Why we taken negative 90 here, minus 90? This is a capacitive, the reactance of the capacitive will be negative. So that graph will be here up to before resonance frequency, that entire will be capacitive system. So that will start from minus 90 to 0. So after resonance frequency entirely that will become inductive. So that will increases to the 90. Okay, so this is about phase angle of the system.